All right, we are now recording. Let's go over just a few of the end game procedures here. Let me get my thing on first. Come on, baby, you can do it. Yes, here we go. All right. Today is the last day of class. So before you leave today, I want to give you all the tests that you've turned in so far. So if you have to leave early, please let me know in time so that I can get you your test back. Okay, so that's one thing. Number two, I will be giving, well, depending on how far we get today, I may give you a very short test on just chapter 18, and if we get into it, 19. Because, as if you remember, I think I said it, when we started this, we're only doing 18.1, which we're almost through, 18.2, which we're going to be starting shortly, and then jump to 18.7. Okay? Now, once we get those three done, we go to 19, and there's only two sections there. 3 and 5. Now, we probably won't get all those done, but we might get some of them. So if we do get far enough, I'll give you a very short test that'll just cover those sections. Now, it may have some questions not in those sections. Those will be completely optional. If you get them right, you get bonus points. If you get them wrong or leave them blank, they don't cost you at all. So we'll see if we get that far today. Now, another thing I've been meaning to ask every class, and I keep forgetting to. Maybe I have asked it at least once. Have you done the student course evaluation yet? Yes? Good. If not, please do those. Now, you can wait till the end of the term if you want to. That's perfectly fine. Just please don't forget to do it. I know when I was an undergraduate, and by the time that last final was over with, it was like an Etch-a-Sketch. Someone shook me and everything went blank, and I completely forgot to do something, so do it, get it done while you're thinking of it. So don't be like me. Okay. So that's that. Student course evaluations. We'll cover whatever we can today, and then once the day's over, I'll pass out all the tests. It'll be too late to turn in any others. So if you are missing a test, by the way, Felicia, you gave me a test you had already done before. I don't know how you got 2 copies of it, but I gave you the better grade. You had almost the same score on both of them. I just gave you the better one. So I hope everybody does have, oh boy, more grading. All right, I'm looking forward to it. Okay. So let me I'll do this for the 4 of you here. Probably won't do it once everybody else comes in. But everybody but one person has turned in test 1. And that person I know has it. She came to see me last week or the week before saying there had been all sorts of family issues and stuff like this, and other issues, domestic issues, and that she was going to try to get things done. I haven't seen her since. Okay, test 2. 3 people haven't turned that in, none of whom are here right now. 4 people haven't turned it in. All of you have. 5 have turned it in, 4 of you are present. Test 3. Now, you may have just turned it in. Was that one that you just turned in?
That was 4 and 5. I already turned it test 3.
Okay, let me see.
You may still have some mixed in. Yeah, that was last class. I turned in 3. That was 4.
Okay.
I turned in 4 last period.
Oh, okay. These are okay. Now I think I'm missing test 3 from. Let me go across here. No, wait. I think I've gotten off the line is what the problem is. Yeah, I've got yours. Okay. I've got the only one I'm missing. I think is Kalicia's. Okay. That's all. It's way on the opposite side of the page, and my eyes went crooked. Okay. So yeah, that's your test 3. Okay. And test 4, I only had 2 in before today, but I just got 1 more in, so that makes 3. And then test 5, I just got 2 in. So test 5, if you don't have that finished yet, you can turn that in with the final, if there is a final, because that may be your last test, depending on how far we get today. But test 4, I do need those in today if you can. So 3 and 4 for everybody in the room here. Some people not in the room, there's more than that, but there's 1 person missing 3, and I think what you did, no, Felicia, I have your test 4. Okay, so it's test 5 is all I'm missing from you, and that you can turn in next week. Okay, so you have test 5 in hand. I hope you do. Does everybody have test 5? Did you get? Okay, you need that. Okay, let me find that. This is it right here. And by the way, for those who weren't here to hear our earlier conversation, number 7 says what voltage is required to produce a current of 2.85 amps in the circuit below. That means the circuit described in number 8, where you have 3 resistors in series with a 36 volt source. This is saying, what if you didn't have a 36 volt, what would you need to provide 2.85 amps? So that's not my original. I want to make sure it wasn't my original. Okay. No, I think that's done. All right. All right. Let me finish this then. So once we finish today, I'll give you, if we do have a last test, I'll give you the last test. I'll tell you which questions are required and which ones are optional, if there are any. I think there will be. And then next week, I will be here, just like always, or as soon as I can, at 4:30. There won't be a class, but it'll be the time for you to turn in your test. Okay? Either 1 or 2 tests or whatever is still missing. Okay? Now, I'll be here from 4:30 to 6:30, busily grading, I'm sure. So, and but if you want to turn in things earlier, let me tell you, okay? Tomorrow, I'm on the Bessemer campus all day, from 8 in the morning till 6 in the evening. So if you want to run by Bessemer and drop something off, I'm in class just about all that time, but my office is in room 265. You can drop off things for me there. Slide it under my door if I'm not in there. If you know where the mail room is there, my box is, I think, number 75, but you probably don't know where the mail room is. If you want to talk with me, just ask someone at the front desk. When I say front desk, this is the desk that you come in once you go around the back side of the building and come in. It's the student entrance, which is student services, it says over the top. The one facing the hospital, you walk in and you're just in an empty hallway. I mean, you're in a hallway, and you're not real clear where to go from there. The mailroom is real close to there. If you knew where the mailroom was, you could put it in my box. But if you come in the other side. Now, here's another possibility. If this campus is more convenient for you and next Wednesday is not, I'll check with Miss, I can't remember her name, in the office. I know it, and I just can't remember it. I know I've got it written down here somewhere. Let's see if I can find it. She's the secretary here. I'm looking in the wrong group. If it's in this book, I think it is. Here we go. Yeah. Oh, Miss Murphy, who's in the office here, the secretary. I'll go out now. Will any of you find that more convenient to drop it by here someday other than Wednesday? Huh? Monday on this campus? Okay. Bessemer's not convenient for you, right? Oh, Tuscaloosa. Well, then, actually, Bessemer campus is much closer. Huh? Do you know where Bessemer campus is? Yeah, you take Academy Drive exit and just come up past the Civic Center.
Yeah, I started over there.
You did? Okay, you know where that is. Then if you just go in the thing and are you familiar enough with the A building that I can? It's room A265 is my office number. Yeah, 265. If you come in the back side of the building where the student entrance is, you come in the new part, go around to the right of the admissions desk, and then before you get to the end of the hall right across from Student Financial Services, there's a gray double doors. Take a right there. It goes through a short hallway and empties into the old part of the building. And when you get on that, you're on the second floor. You were on first floor, now you're on second floor. You didn't go up or down a single step. And then take a right on that old hallway. The last door on the left is not the stairwell, but the last office on the left is mine, 265. So if you want to drop it by there, what time would you think? Second? Around 1. Okay, I'll probably still be in class then, so slide it under my door. I'm in class, let me think. Monday. Oh, no, wait. Monday's the final exam day. I'll probably be around the office. So, yeah. I'm not having it. No, wait. No. Monday is a class day. Monday is a class day. Wednesday's not, but Monday is. So, on Monday, I have class from 10 until 11:40.
Monday is a class day?
Yeah. Yeah, it's bizarre, but for Monday, Wednesday classes. It's the last class day. But we're a Wednesday-only class, so that's why today's our last one. So I'm in a class from 10 to 11:40, and then from 12:30 until, so I'll be in class around 1. So, what's that?
I'll just bring mine to Wednesday.
Or just slide it under your office door, regardless.
What's that?
I just put it
Under my door. That's a good idea. You'll see my name and everything. Make sure it's my office door, but it's posted all over it. And slide it under there, and I'll pick it up. Okay. And if you don't finish it by then, Wednesday will be fine. I'll be here. But you know, Bessemer campus is real close to Tuscaloosa. I mean, much closer than this is. Okay. So even if you want to bring it Wednesday and slide it under my door there, after I'm over here, that will be fine. I'll pick it up Thursday morning. So, but if you can't finish it, as long as you get it to me, so if you can't get it here by Wednesday afternoon, next Wednesday, I'll be here from 4:30 to 6:30. After that, Thursday, I'll be on the Bessemer campus all day, 8 to 6. Second?
It's too far.
Yeah, 8 to 6. And then on Friday, I'll be back here on Birmingham campus, where I'll be on the West campus over there in the B building. And it's Dr. Pruitt's office. This will be this Friday and next Friday from 8 to 12. And that's it's B122. And it's the end of the B building. The B building, academic building, the long building there, the one toward the gym, tennis courts, and baseball field, the end of the B building. As you come in the door, you either go down half a flight or up. Go up half a flight. When you're on the top step, the room immediately to your left is 122. And I'll be there from 8 to 12 on Friday. Probably longer and probably before 8, but those are my official office hours. Then Monday of that week, that's the last day technically of final exams, I'll be Bessemer campus 8 to 6, all day long, 8 to 6. And then Tuesday, you can also bring them by Tuesday, Bessemer campus 8 to 6. But Wednesday, I have to have the grades in by noon on Wednesday. So if I don't have them by noon on Wednesday, you're getting an incomplete. But I think y'all will all get it. Y'all been getting everything in on time, so I'm not worried about that. The people not here that I'm talking with there. All right. Any questions then on that? Okay. Let me go back to, so none of you wanted to drop it off here at the office. Is that right? Yeah, the nursing office right across the hall. You're going to be here Wednesday.
Yeah.
Okay. Okay. That's preferable. But I was thinking if that was inconvenient for somebody, then I could manage to work around that. Okay, I could get Miss Murphy to hold it for me. I'd pick it up Wednesday. Okay. Or pick it up later if you let me know. Okay. Now this is where we left off. Any questions so far? Chapter 18 or before? Anything? Any questions so far? If not, in chapter 18, magnetism, we're in the very end of 18.1. I can't remember the title of that. It's Introduction to Magnetism, good title. And we're on this last slide in this, and this is this slide right here. It's just an interesting, confusing, whatever thing about our poles. The North Geographic Pole goes right through the North Pole, okay? That's the axis around which the Earth spins, the actual North Pole of the Earth. However, our magnetic North Pole is off from that a little bit. It's over in, this is Hudson Bay down here, this is Greenland here, this is another set of water and islands and stuff in the very northern part of Canada. And right somewhere in the middle of all that water, those islands, is our actually magnetic North Pole. Okay? So there's a little bit of offset, not much. I think it's only 2.5 degrees, something like that. So therefore, if you have a magnetic compass, if you are in a place where it lines up, that those two line up, the magnetic compass is going to point straight toward due north. That line in the U.S. goes almost through Atlanta, Georgia. So we're just a little bit off from that. So we here in Birmingham area, we're about 2 degrees off. Not far at all. Okay? So when you see a compass pointing north around here, it's really close to north. It's not very far off at all. Some places over in Maine, they'll be off a lot more. And on the West Coast, off a lot more. Still not a whole lot, but we're within 2 degrees. So we are very, very close. Our magnetic north to the true north. Okay. Now in the south hemisphere, southern hemisphere, the south magnetic pole is even further off from the south geographic pole. I don't know why that's the case, but it's still not too far. But these are relatively close. The ones down here, a little bit further. And they sort of, well, they make it seem like they're the same, but they're off just a little bit further than we are, than the northern hemisphere. Okay? So, let's see if there's anything else we need to know here. Earth's magnetic is similar to that of other magnets. The geographic and magnetic poles do not coincide. Similarly, geographic and magnetic equators are slightly different. The needle and compass points to the north magnetic pole, not to the true north. Now, if you happen to have a compass they call a gyrocompass, those are based on gyroscopes, those point to true north, not to magnetic north. We have those on naval ship vessels, and I don't know about aircraft. I imagine they do, but those can get out of, they have to be spinning pretty rapidly to stay true, whereas a magnetic will be, it's always going to point to the magnetic North Pole. All right, that's the last, well, no, it isn't, is it? Oh, that's the last slide in 18.1. We're now moving to 18.2, which is magnetic effects of currents. Now, yeah, that's, I have to go back and remind myself. Yeah, we do 18.2 and then jump to 18.7. All right, and this is what we're talking about here. Let's see if there's any, yeah. There was a guy, when current passes through a conductor, it forms a magnetic field. A compass placed near that current shows the direction of the magnetic field, and this was first discovered by Hans Christian Ørsted. Okay? All right. And is it Cerdarius? Okay. All right. Now, hate to have to do this for people who've already heard it before. Let me say this. All your tests have to be in today, all the ones you have, except test 5. Test 5 you can wait and turn in next week. That may wind up being your final, but if not, you can turn it in with the final. So I need 1 through 4 in today. Otherwise, they're zeros. Okay, and that's going to be hard to pull out. Okay? Huh? All right. So I need them all in before the end of class today, because I'm going to be returning all papers by the end of class today. Okay? Now, and I will be, if we do have a final today on this, I'll be passing that out at the end of class. Test 5, you can turn in. I handed that out, what, last week or week before? Last week. So you can have an extra week on that if you need to. But you can turn that in with the final, or it may wind up being the final. So Hans Christian Ørsted, pretty certain he was Danish, born in Denmark. He was the first to discover this connection between electricity and magnetism. Before that, people thought they were completely different, separate, no connection at all. And here's basically what is being said here. Let's just say that we have a battery. Looks like a 9-volt battery here, okay? Positive, negative, okay? Now, if the switch is open, the compass points to the true north, or magnetic north anyway, okay? Because there's no field being produced by the wire. There's no current through the wire, okay? But if you close this switch, and now the current begins, that's the I here, the current starts flowing. Now, here's the rule for the current, okay? If you put your right thumb in the direction of the current flow, your fingers on your right hand are going to wrap around, showing you the direction of the field. And remember, the field lines go from the north toward the south, and that's where we're going here. Your thumb is in the direction of the flow, and your fingers are pointing from the north to the south. So suddenly the compass thinks north is that way, because it's found a stronger magnetic field that is produced by that current in the wire. So let me give you one principle of electromagnetism that ties the two together. A moving charge induces a magnetic field. Always. A hree basic naturally occurring magnetic materials. Anyone remember what they were?
The solid. Oh, you talking about the
Naturally occurring magnets. Iron, nickel, and cobalt. Now, wait a minute. Every element has electrons moving around it. So why do they all produce magnetic fields? Because all materials, even hydrogen, only has one electron. That could be anywhere. It doesn't follow a set pattern. So therefore there is no magnetic field. Iron, nickel, and cobalt, there's something about the way their electrons are oriented so that they do produce a magnetic field. Always. Every atom produces a magnetic field. However, every piece of iron, nickel, or cobalt isn't naturally occurring magnet. Why? Because their atoms are arranged at all sorts of ways. So this field will cancel that, and this and that. So generally they're not magnetic. But iron, nickel, and cobalt, if you put it in the presence of a magnetic field, those atoms line up with that field. Okay? That's why you can make an electromagnet with iron, nickel, and cobalt as a core. We'll get to that a little bit later. Okay? That's also why when you stroke a piece of iron, nickel, or cobalt on a magnet, the stroking of it rearranges and joggles those domains, they call them, until they do line up, and then they get permanently fixed. And that now becomes a magnet. I don't know if you've ever done it before. Get a regular old needle that doesn't attract any iron filings or anything else, and stroke it on a magnet, and then put it in iron filings, it'll be covered with it, because you just made a magnet out of it. But you have to have that perturbation, that shaking of the domains forcing. Here you don't need any shaking at all. It's the moving charge. Moving charge induces a magnetic field. Now, what if you reversed and put the wire coming that was here, move it to negative, and the wire that was on negative, move it to positive, so the current flows this way? Well, take your right hand, put it in the direction of flow, points away from, and the compass is underneath. The current's flowing this way, right hand. Now the north is pointing in this direction. So the needle actually flips, okay? Because now you've created the magnetic field in the opposite direction, okay? Now, open it again. Open the switch. It goes back to wherever true north was, okay? Now, okay. The compass was beneath the wire. So here, the wire field is like this, going underneath, and so right hand points. I'm sorry, I said it backwards before. Points. The compass lines up with the south pole. Okay. The north magnetic pole is pointing toward the southern pole of the compass, which would be like this, okay? And then when you reverse the current, it changes. You put it on top and open this. Now the field lines are pointing like this, so that's north here. This way they're pointing north that way. So you see they change whether you're on top or beneath. You can take the compass and move it anywhere around there, and you'll find they always point this way on top, that way underneath. Unless you reverse your current, and then they're this way underneath and that way on top, wherever you go. So you see your field lines, they actually form little concentric circles, just like your fingers do. And that's the magnetic field. Okay? First discovered by Hans Christian Ørsted. Okay? Now, the field actually curves around the straight current-carrying wire. If you put the wire straight up this way, here are the field lines. Again, the current is moving up. This is called the conventional current, the direction positive charges would flow if they flowed. Pointed up, then the field lines, your right-hand rule says the field lines point in this direction. There's the right-hand rule here. The fingers wrap in the directions of that. So there's the field lines. Now, let's take that concept. Oh, I heard something, but I didn't see you. Here is Trent, right?
Yes, sir.
Okay. Sorry, team. Let me repeat again, because I want everybody to hear this. At the end of class today, I'm returning all the tests that have been turned in so far. That's the first 4 tests, should be. Okay? If you haven't turned them in by the end of class today, that's a 0 on that test. It's going to be really hard to overcome. So I need them all in by the end of class today. I'll be turning papers back. Now, the 5th test I gave out last week. If you weren't here, you need to get that one. That's due technically by next Wednesday. I will be here from 4:30 to 6:30 next Wednesday just to pick up tests. There will be no formal class then, but I'll be here to pick up your test. You can do test 5, and if we do have a test 6 at the end of class today, we'll determine that, whether there will be a 6th test. I'll pick up both of those next week. 2 people turned in test 5 tonight, so I'll take test 5 if you finish it, but otherwise 5 and 6 are due next week. Okay? Test 6, if we have one, it'll be due next Wednesday. I was also telling the others, if next Wednesday night here is not convenient for you, I'm on the Bessemer campus. Let me just tell you, it's in the syllabus and everything else, but I'm on Bessemer campus tomorrow from 8 to 6. I'm on Birmingham West Campus, right across here in the B building, the academic building, in Dr. Pruitt's office. That's room 122. I'm in there Fridays from 8 to 12. Okay, I'll probably be there earlier or later, but those are officially my office hours. Then Monday of next week, I'm back on Bessemer campus from 8 to 6. Monday of next week is the last day of class, so I won't be in the office the whole time, but I'll be in my office or classroom. You can slide her under my office door anytime you want to. Okay? Tuesday, I'll be on Bessemer campus, 8 to 6. That's the first day of finals, so I'll be in the office. Well, I have a final from 8 to 10, and then I'll be in the office other than that. And then on Wednesday, I'll be on the Bessemer campus from 8 to 4. And I'll be driving over here and be here from 4:30 to 6:30. Thursday of next week, on Bessemer campus from 8 to 6 again. Now, time out just a moment here. Are any of you graduating this term? You two are. Okay. That means I have to have your finals, whether it's one test or two, whatever you don't turn in tonight. But it's 5 or 6. 5, I know for sure. 6, if we have a test 6. I have to have yours by Thursday of next week. I can't wait until Monday or Tuesday of next week, because your grades have to be in by noon on Friday. Okay? All the rest of you are not graduating this term. Your grades are due in Wednesday of the following week. So I can't take yours up until Monday. So I've got to have your finals in. Otherwise, your grades aren't there. You may not be graduating this term. So please do that. Forgot to tell you that. Do you know if Kalista is graduating? I don't think she is. Okay. Because I didn't say that while she was in here. All right. Now, we've talked about the field lines here. The field actually curves around the straight line, just like I showed here. Iron filings, if you put them on that sheet of paper, you see they all line up in these concentric circles. Those are the field lines. Okay? The magnetic field is stronger for large currents than for small currents. The direction of the field near a current in a straight wire is given by Ampere's rule. And that's coming up next. Okay? Oh, I'm sorry. Ampere's rule is the right-hand rule. Okay, sorry. That was it. There's also Ampere's law. I thought they're not showing Ampere's law. Okay. Top of page, that's on 506. 507, the magnetic field near a long current-carrying wire measured in units of Teslas. Teslas. Tesla. Okay? The magnetic field, let me get my pen set up. Okay, magnetic field is actually 2 units for it. The SI unit is Tesla. Okay, that stands for T-E-S-L-A. The old unit for it was Gauss. That's G-A-U-S-S. Gauss. Okay, both of those are capitalized. Why? Named after somebody. Nikola Tesla was a very, incredibly bright scientist and engineer, born in Croatia, which was later part of Yugoslavia, and then now is Croatia again. Came to the U.S. and actually worked under Thomas Edison. And they collaborated, and really, they were dynamite together, except they were also explosive, okay? And when they disagreed, it was major. When they worked well together, it was major. And after a while, Tesla went off on his own. Tesla believed AC current was what the future held. Edison was convinced DC would be it. Well, Tesla and another guy named Westinghouse, they won. AC was the way we do most of our electricity. Of course, anything that runs on a battery is DC. So we still have a lot of things that are DC. Laptops, iPhones, all these things. Of course, you plug it into an AC circuit, But what do you have in between that and the computer? A black box or a white box or a little box, some type of box. You have a plug-in on yours? Oh, you don't, do you? Okay. If you have, you know there's a little plug that plugs into the wall. It's a little square-looking thing. That's what this is, okay? It changes the AC coming in to DC going out. And you'll notice the wires are different. Well, that plugs into the wall. It doesn't have a wire there. It plugs directly into the wall. But that's the case. This is what they call a converter, or this is actually called an adapter that adapts AC to DC. In your car, just about everything is DC, except your generator is generating AC. But you have a device in your car called an alternator that changes it back to DC. That's so it can recharge your battery. Okay? AC would discharge charge. It would never get it recharged. But your alternator makes it all DC. So it can recharge your battery. Okay, Nikola Tesla is mentioned in your book, given a nice little blurb here, 1856 to 1943. Brilliant guy. He and Westinghouse worked together for quite a bit. Tesla did so many things. He was a brilliant scientist, but a pretty lousy businessman. He basically wound up broke all the time because he would spend his own money on new projects and stuff and wouldn't get funding and wound up broke. His ideas were great, but he couldn't afford them, okay? Other people would buy them like Westinghouse did, and he would have a little money for a while, but then wound up broke again. All right, but here is... well, this actually is Ampere's law. It's just not the one that I was thinking it was going to be. Here is Ampere's law. B, and that is your magnetic field measured in Tesla or Gauss. This would be in Tesla. B is equal to mu naught. That's a constant of nature. I'll tell you what it is in just a minute. Times the current, because there's got to be a current. Otherwise, there's no magnetic field. Moving charge creates a magnetic field, divided by 2 pi. Those are both just numbers, okay? R, capital R. R is the perpendicular distance from the center of the wire. So R would be the distance here, the distance there, the distance there. You know, whatever distance, these would be various R's, okay? The distance from the center of the wire. Okay. One thing I forgot to say earlier, but I wanted to say it now. You're not graduating this term, are you? Okay. Students who are graduating this term, I have to have your finals in by Thursday of next week because your grades are due in Friday noon. But the rest of you, if you can't get it to me Wednesday of next week, you can give it to me as late as Monday, because your grades don't go in until Wednesday at noon. Okay, so that gives me one day to get the grading done and things on Blackboard and averages done and all like that. Okay, so this is Ampere's law. B is there is another Ampere's law, but we won't, either it's not going to show up now. It had to do with forces. This has not got to do with forces. This is magnetic field. Okay? Now, let me tell you what this mu is. That's a constant of nature, and it's 4 pi times 10 to the 7th, 10 to the negative 7th, and that's units of Tesla meter per amp. Okay? That is your proportionality constant. Because you see, you have amps up here, that cancels that amp out. You have meter down here, the radius in meters, so that cancels that out. And Tesla is what you wind up with over here, Tesla. So you want that in the numerator. 2 pi has no units at all. So there is Ampere's law. Okay? Ampere's law. There is another thing called Ampere's law, which has to do with forces. This is it. Okay. Now, they have something not quite written right in the book. On the right hand it's right, and the wording should be right, but let me point it out to you. Okay. Oh, I'm sorry. It is okay. Yeah. This B has another name. That's what it is. It is the magnetic field strength, but it has another name, and it's called magnetic flux density. I can't write well. Rather strange name, okay? That is your B, another name for B, and that is given in units of phi, which is what we call magnetic flux, okay, divided by A, which is your unit area, okay? So in other words, what we're talking about here is if you took an imaginary area and you put up here, then the flux density would be how much flux is going through that area, okay? And that was another way of calling your field strength, okay? Rather a strange way to describe it, but it's certainly there. And by the way, a unit Tesla, which measures field strength, magnetic field, or flux density, it has the units of, it says W per meter squared. And I'm pretty sure that is watts, though there is another term called a Weber, and I want to make sure that's not a Weber. I'm pretty sure that is a watt. Okay? Yeah. So 1 Tesla, where is it? I had it written there. Oh, no, there it is. Okay, a Tesla has units of watts per meter squared. No, it's not watts. That's a Weber. Okay, it's got to be, because that's flux density. It's got to be a Weber, but they never say it here, but that's what it is. Now, if you're dealing with square meters rather than square centimeters, then that's where you get your Gauss. That would be Webers per square centimeter. And that was the old way they measured it. Much smaller unit. A square meter is huge. It's basically this long, this high, that, well, no, that would be it. It's the bottom part of the door, from the doorknob down. That's about 1 square meter. It's a huge area. Square centimeter is about like this. You know, your little finger across and high. That's a square centimeter. And that would be Gauss. Much more convenient measure. But because SI units are based on the big ones. So a Gauss is, and this formula they have here, I can't make any sense out of. They say mx per centimeter squared. And I'm not sure what their mx is. It just doesn't make sense. It should be watts per centimeter square, but they have mx. I don't know what that means. So let's do example 1. So let's get out of this slide and go back to this one. Okay, and we'll go from current slide here. All right. A power line carrying 400 amps. Man, that's a lot of current. Okay, so here's a power line. Oops, I got to get my color back. Okay, here's your power line, and it's carrying 400 amps. And they say that last zero is significant. So, is 9 meters above a transit used by a surveying student. So somewhere down here, way down here, is a surveying student trying to use a transit, which is a device, okay? And this is 9 meters above him. 9 meters above him, okay? 9.00 meters above him, okay? Find the magnetic field formed by the power line above the transit. Okay? Well, what we have here is B. That's what we're looking for. Find the magnetic field. That's B. That's the unknown. That's what we're looking for. And that's equal to, I wish I still had it up here, mu naught. That's a constant of nature. By the way, that is given a name. I'm trying to, it's a rather weird name. It's called the permittivity of free space. And I don't see it in your table at the back of the book either, but it's called the permittivity of free space. Weird title. So anyway, I'll leave that. There it is. Well, it's a permeability constant is what they call it here. Otherwise known as permittivity of free space. Okay? So that's mu naught times your current divided by 2 pi times the radius. Well, this is your radius here. How far you are from the line. Okay? Your current, that's this. 400 amps. Woo, huge amount of current. Okay? And your mu naught, remember, was 4 pi times 10 to the minus 7th, was it? Yeah, minus 7th. Tesla meter per amp. Okay? So let's plug and chug. 4 pi times 10 to the minus 7th Tesla meters per amp times 400 amps. Therefore, your amps are going to cancel out. Divided by 2 pi. And the 2 pi will go in the 4 pi twice. So that goes away. And then you have your radius of 9.00 meters. Because that's how far it is above. So here you see your meters go out. Okay? Now, 400 times 2 would be 800 divided by 9. If someone will punch, oh, yeah.
88.88.
Say again.
88.8888.
Okay, make it 0.9. Okay? And that will be Tesla, because that's the unit that you have left over. Okay? Let's see how they did in the book. Oh, wait, you forgot your 10 to the minus 7th, didn't you? Here's the 10 to the minus 7th. Times 10 to the minus 7th. I forgot to write it down. So this will be 8.89 times 10 to the, see, we made that number smaller, so make that bigger by, make it minus 6. Which then, and that would be Tesla, and you could write that as 8.89 times, and make that micro Tesla, because 10 to the minus 6 is micro. Let's see if that's what they got in the book. 8.89 times 10 to the minus 6 Tesla, which you could call it micro Tesla. So a Tesla is a pretty good size magnetic field strength, magnetic field, but 9 meters away it's going to drop off like crazy, okay? And so, but even if it was right on it, that would still be 10 to the minus 5, so it would only gain 1 order of magnitude. So a Tesla is a really strong field strength. So this, 9 meters above, hardly going to be problematic. Now, here's an issue though. If the Earth's horizontal component of the magnetic field is 5 so we'll call the B, so this is the B for the power line, okay? Power line. This is B for Earth. If the Earth's magnetic field is 5.2 times 10 to the minus 5 Tesla. Okay, that's considerably stronger. Okay, at that location, what error could be introduced in the angular measure? Assume the power lines runs north-south, so it's going to have the maximum effect. Well, what's the difference between these two? 5.20, that, by the way, is 52.0 times 10 to the minus 6 Tesla, and subtract from that 8.89 times 10 to the minus 6 Tesla, and you get 43.11, yeah, times 10 to the minus 6. So there's the difference, and it says what error could be introduced. Sorry. Yeah. No, I'm sorry. You don't need this. They're asking for, I think you just divide 8.89 by the 552. Yeah. Whoa. They're calling it an angular error. Okay. Don't sweat this. I'm going to show you what it is, but it's the tangent of theta. Now, have any of you had any trigonometry? High school or anywhere? None. Okay. It's not required for this course. It would normally be required for a physics course, but this course doesn't require it. But what that is of a right triangle, it's the opposite side over the adjacent side. Okay, that's your tangent. Okay, so the tangent would then be, like I said, this ratio of 5. Except they're putting that. Oh no, okay. It's 8.89. I knew it had to be that way. 8.89 times 10 to the minus 6 divided by 5.20 times 10 to the minus 5th. Okay? And that gives you 0.171. Now, they're telling you that, and I'll believe it looks about the right magnitude. And if you take so that's the tangent. What you do is an inverse tangent. On your calculator, if you see a key that says tangent to the minus 1, that's the inverse tangent. If you press that key with this as your information, that gives you an angle of about 9.7 degrees. So it would have a significant variation on that. You're not required to do tangents and inverse tangents and stuff like that, so don't sweat those, okay? But that's the bearing of the student's transit could be an error by 9.7% because of that. That would be the maximum. Well, it sounds pretty big, okay, if you're trying to do detailed survey. So you'd have to watch out for that. All right. Let's go back to the other slide and see if what they have next there. Okay. Coming up, but not quite there. So let's go back to the one before. Okay. Now, if a wire, okay, we mentioned a wire, a straight wire, going up with a current running through it. The field lines would go around it like this. That's pretty weak field. You need an awful lot of current, like 400 amps, to create very much of a magnetic field. But what if you took that wire and wound it into a coil? Now think of that wire, okay? I'm going to let my thumb follow that wire along, and the field lines are doing this, and this, and this. Notice they're always pointing toward the center of that coil. And if you have a bunch of them, you're adding those up and adding them up and adding them up, whereas before you just measured one strength. Now you're adding all the way around and as many coils as you have. So you can really build up a very strong magnetic field. Very strong magnetic field with relatively small current. Okay? And that's called a solenoid. Okay? And they have the picture in the text. I was going to try to draw it. My drawings stink though. Okay? So here's the wire. I've got to get my pen back. Okay? We have the current going in this direction in the wire. There's the current going in the wire. This is I. Okay? Right-hand rule, point the thumb in the direction of that, and the field is going like this. Just like your fingers, you know, going around like this. Okay? Now, make a loop out of that, and boy, it gets crazy. So have your wire going like this, but then make one loop and come out. So again, your current's flowing in this direction. So you have the field going like this, the field going like this. But now all around here, the field's going like this, and it's all pointing up toward the center and then back around and back around. So you get a much stronger field around that one loop than you do in a straight wire. Much stronger. Okay? To determine the direction of flux lines in a current loop, use Ampere's rule. Okay? If several loops are made in a tight spiral, as shown in figure 1614, so let's go back to that one. Have to go through all this again. This is what we call a solenoid. Let me get my pen back. Okay? A magnetic field from a coil. If you put iron filings there and have the coil running through a piece of paper, look how the iron filings have lined up, just like the field lines. They show the field lines here. Now, what they say here is wrap your fingers around in the direction of the coil. Okay? Let me see. This is in the book here. Looks like they've said it wrong. Hold the solenoid in your right hand so that your fingers circle it in the same direction as the current. Then the direction of your thumb points indicates the northern orientation of the solenoid. So your current, yeah, now I see. Here's the current flowing in this direction, so your fingers are doing like this, because they're going back and around. So your fingers are doing that. There's the north pole for the solenoid. You'd have to know which way the current's flowing and which way the coils are going, and that gives you your north pole here. Now, if you had a bar magnet, that looks just like a bar magnet. Concentration of filings here and here, here and here, and weaker out here. Hardly any orientation here. The field lines go like that, but your great concentration here. So the greatest, the strong north pole here, strong south pole here. Okay? The field line goes away from north toward the south. Okay. Now, what this is showing, a little coil of wire, not a very organized coil of wire, but a little coil of wire, and I assume that this is the positive coming this way, but I can't see which way it's done. But if you look at the compasses here, see the compass needle is pointing this way here, that way there, that way there, that way, that way, that way, that way. So you see the field lines are very, very strong. Strongest here, you know, they're just up and down here, very weak there, the strongest right there. Okay? So there's your solenoid. To me, that last is a pretty lousy illustration. Okay? But you can see that the compass needle is turning. What you don't see is the battery. You don't see which pole is that. You don't see much of anything. So, A compass also represents the magnetic field around the wire. So that's the solenoid. That's the figure on the bottom of page 509. Now, let's see. We'll come back to this one later. Come back to that one later. Get away from this and go back to this one. Okay, we'll go back to current slide. Here we go. Now, for a long coil that is tightly turned, the field strength at the center is given by this formula. Get my pen back. B, that's the magnetic field strength, or flux density, okay, is equal to that good old mu naught, constant of nature, times the current, times N, where N is the number of turns per unit length of the solenoid. So if you have a fairly short solenoid with lots of turns in it, it's going to be a large number. A longer solenoid with fewer turns, that'll be a weaker. It's number of turns per unit length of the solenoid. Okay? So that can vary depending on how you made the turns. Okay? Mu naught is still the same thing as before. I is still current. N is the new feature here. So let's do example 2 while we're on the page. Find the magnetic field at the center of a solenoid that is 0.425 meters long. Okay? So that's the length of the solenoid. Let's just imagine that's the solenoid. This is the length. From here to there is the length. L is equal to 0.425 meters. Pretty long solenoid, by the way. Okay? And 0.750 meters in diameter. Now, we didn't have anything there. This is 0.075, is that right? 0 meters in diameter. Oh, diameter. I would put radius. There's the diameter. Diameter of the solenoid. It has 3 layers of 850 turns each. So 3 layers, 850 turns each. Okay. Let me get... Okay. Let's look. The Tundra, is that right? Yeah. Okay. Now, sorry, let's have a timeout again, because I want to make sure everybody hears this, okay? All of your tests that we've had so far, 1 through 4 anyway, have to be in by the end of class tonight, okay? Because I'm going to be returning those to you tonight. This is the last day of class, okay? The test 5 that I gave you last week, you can still work on that and turn it in next week. That'll be fine. If I give you a test tonight, which depends on how much we get to cover in chapters 18 and 19, if we do get enough to cover, then I'll give you test 6. It'll be very short, very quick. The test 5 is a pretty reasonable test, but this one will be a little bit shorter, okay? I will be here, just like always, from 4:30 till 6:30 next Wednesday night. So if you want to turn in your tests then, 5 and 6, or just 6, if you've already turned in 5, we're going to turn it in tonight. I'll be here to get it then. If you need more time, if that's not a good time for you, okay, let me give you the other times. Don't think anyone will be ready to turn it in tomorrow, but if you are, I'm on the Bessemer campus from 8 to 6 tomorrow. I'm in class just about all that time, so slide it under my door in room 265 in the A building, A265 Bessemer campus. Friday, I'm here on the Birmingham West Campus, the other side of Wilson Road, and I'm in B, that's the academic building, B122, in Dr. Pruitt's office, Friday from 8 to 12. Monday of next week, I'm back on Bessemer campus, 8 to 6 again, but I'm in class from 10 until 3:45. So 8 to 10, I'm free in my office, and basically 4 to 6, I'm free in the office. In between that, most of the time I'm in class. Okay? But you can slide it on my door at 265. Okay? Tuesday of next week is I'm in a final exam from 8 to 10 in the morning, and after that I'll be in the office just about the rest of the day, from 10 to 12. Bessemer campus, A building, room 265. My exam is in a different room, but you can slide it on my door if I'm not in the office. That's Monday. That's Tuesday. Wednesday, I'm on Bessemer campus from 8 to 4. Okay? I'm not giving any exams, so I'll be in the office that time. From 4 to 4:30, I'm driving here. And 4:30 to 6:30, I'm here. And then I'm heading home. Okay? So that's Wednesday. Thursday of next week. Now, are you graduating this term? Okay. If you're graduating, you have to have your test in by Thursday. Okay? Because I'm grading it. I have to have your grades in on Friday. Only 2 guys are graduating this term. So they're going to have theirs in. If you need more time, Thursday I'm on the Bessemer campus all day. I don't have any finals, so basically 8 to 6 on Thursday. Bessemer campus, room 265. If I'm not there, slide it under my door. A265. Friday again of next week, just like Friday of this week, Birmingham West Campus, academic building B122, from 8 to 12. Monday that's the last day of finals technically of the following week. I'm on Bessemer campus 8 to 6 in my office basically all day long. Okay. Tuesday I'll be on Bessemer campus all day long. I'll be grading papers and stuff like this. So if you don't get it to me any sooner, you have to get it to me by Tuesday. Because Wednesday at 12 noon, everybody's grades go in, except those 2 guys, theirs go in on Friday. And then after grades go in, that's all, folks. Now, another thing, and some of you have come in since I said this, I'm glad I thought of it. How many have done the student course evaluations? All right, some have. Okay, if you haven't, please do those before the end of the term. You can wait until you see the final, even see your final grade, but just please don't forget to do the student course evaluation. If you can do it earlier and feel comfortable do it earlier. Okay. All right. Let's get back to this problem. What we're looking for here, here's what we've got. We're looking for the magnetic field, so B is what we're looking for. B is magnetic field. By the way, it's a vector quantity, but we're not really using it as a vector, but it is a vector quantity. Find the magnetic field at the center of a solenoid that is 0.425 meters long. There's that dimension. 0.0750 meter diameter, so very thin diameter. Has 3 layers, that's what I've written down here. 850 turns each, and that 0 is significant. When 0.25 amps flows through it. So you got I equals 0.250 amps. Okay, so there's your current. Flows throughout. Okay? Now, we've got our formula here. Mu naught is 4 pi times 10 to the minus 7th Tesla meter per amp multiplied by I, which is 0.250 amps. Okay? So your amps cancel out. What we don't have is our N. And the N is the number of turns per unit length of solenoid. So we have 850 turns each in 3 layers, so that's 3 times 850. So that's 0, 5, 24, 25. 2550 turns. Okay? And it says per unit length. Per 0.425 meters. Now notice we haven't used that diameter at all. Okay? And it's okay. What that tells you, the length is far longer than it is this cross-sectional area. That means it's a long, narrow solenoid. So that means we can use this formula, because this formula was good for a long coil, tightly turned. So the length is a great deal more than the diameter, so that's called a long term. So what this is your N right here, is turns per unit length. So this is your 2550 divided by 0.425. And there's your meter here, and that cancels that meter out there. Okay? So if you punch in the numbers, 4 pi, you can find your pi key on your calculator, times, so that's your EE or EXP, -7, times 0.25, times 2550, divided by 0.425. You're going to see this time this B is pretty large. I mean, not huge, but it's much. What do you got?
I'm figuring that out.
What they have in the book is 1.88 times 10 to the -3. Now, it still sounds like a small number, but remember the last one? The last one was 10 to the -6. So this is 1,000 times stronger magnetic field than you had from that power line with 400 amps. This has 1/4 of an amp. That's a huge difference, okay? 400 times 4, that'd be 1,600 times more current, but this is in a very tight coil. So yeah, it's a much stronger field. Did you get anything close? Okay.
Mine's got an error too.
What's that?
I keep on getting an error message.
Oh, wait. Now, part of it is, I didn't do the calculation here. Oh, they said 3 times 850 divided by 0.425 is 6,000. So, yeah, our calculation, I think, is right. Let me see what you got.
I don't know. I cleared it out.
Okay.
So we got 4, 5, and
No, you do the EE or EXP.
1 time.
And then -7. Yep, got it. That's right. Times. Okay. What did I have next? 0.25. 0.25 times 2550. 2550 divided by 0.425. Yeah, and if you move the decimal 1, 2, 3 places, there you have it. So you got 0.00188, which is move the decimal 3 places, and that would be 1.88 times 10 to the -3 Tesla. Much, much, much stronger electric field, magnetic field than we had on the previous example. Okay, that finishes 18.2. And there are some problems here. Do any of the odds that are in the back of the book, 1 through 13. All right. Now, I wish we had time to do more, but we don't. 18.3 is talking about induced magnetism and electromagnets. Basically, what an electromagnet is a solenoid, a coil of wire that you put an iron core or a ferromagnetic core in, and boy, that becomes a very strong magnet, stronger than any permanent magnet you can create. Okay? And that's where I'll just show it to you quickly. this field here is. Okay. Okay. See, if you have unmagnetized iron, your domains are in all sorts of directions. They cancel out all the magnetic. Every iron atom is a little magnet. But when they're randomly distributed like that, you have no magnetic field. But if you have a slightly magnetized iron, maybe you struck on a magnet, and now you have more of them lined up this way. So you got 4 this way, 2 this way, 4 this way, 2 this way, 1 that way, 2. So you got more of them pointed that way. That's a weak magnet. You have a stronger north there, nothing there. They're all over the place. But then you put in a coil of wire like a electromagnet, you line almost all of them up, you have a really strong field. Okay? And that's why electromagnets much, much stronger than permanent magnets. Okay? Now, they have, let me just go through some of this. Oh boy, we can't do this, but what we can do is what they call inducing a current. Now, we're not covering 18.4. That wasn't in our description. We're jumping on to 18.7. So I'm just going to go through it real quickly. Anytime, okay, I'm going to give the other half of the thing. What creates a magnetic field? A moving charge. Anytime electric charge is moving, it creates a magnetic field. Most times they're very, very weak, but if you have enough charges moving, you can build up a pretty strong magnetic field. That's what's happening in iron, nickel, and cobalt, but they're the only ones that do. Okay? Now, on the other side, if you have a changing magnetic field, you can create a current. A changing magnetic field creates a current. A moving charge creates a magnetic field. So the yin and yang. One creates one, one's another. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They go back and forth like that. And that's what they're talking about with induced currents. Okay? And this picture here is showing how a generator works. And that's 18.5. But we're not doing 18.5. We're jumping to 18.7. So you aren't responsible for that, but there it is. Okay? You can make a DC. This was an AC generator, I think. No, this is a DC generator. Okay? I'm trying to see what the difference in these two slides are. I really can't see a difference. Can you? Oh, I see. They've changed the direction of turn. I think that's what it is. Wait. No? Turn the same way. Oh, but it's just showing when the brushes are flipped across, they change the current. Okay, that's what they show. But you're not responsible for that. Okay? Now, that was a generator. The opposite of a generator is a motor. What a generator does is take mechanical energy and creates electricity. What a motor does is take electrical energy and creates mechanical energy, like your lawnmower if you have electric weed eater or something like that. And here is something that is indeed true. This is the principle that a motor runs on. If you have a permanent magnetic field represented by permanent magnet, and then you have a electromagnet that's turning, and if every half turn it flips its field, that keeps the motor turning, because the North Pole repels the North Pole just like this, okay, and North repels North, so it's going to turn that way, and as soon as the South gets here and wants to stop, then it's going to flip it again, and that gets it turning again. You have to have what they call as a commutator, and I'll go back a slide and show you. This is a commutator here, As soon as you go half a turn, it flips the current, and that's what these two slides will show. One half turn is going one way, the other half the other way, so it's flipping it every time. And if you have that in a motor, which you do, then the motor keeps spinning in the same direction. And electric motors are generally pretty efficient. But you don't need to know it. That's just your, that was 18.6, the motor principle. All right. 18.7, this is the one slide in it, and that's all we do. This we are responsible for. But there's no problems to work here, so this is all you got, folks. Remember I said two things. A moving charge creates a magnetic field, and a changing field creates current. Okay? Yin and yang. Okay? So if you have an electron beam, that's a moving charge. Electrons have charge moving. If you put them through a magnetic field, it's going to deflect them. Okay? And that deflection is what we can measure, and that's how we do things like measuring the mass or the momentum or anything else of things that usually are too small to measure. We do that. Now, I know that y'all are doing sonography, which is only the sound part, but you know there are other techniques that do magnetic resonance imaging, MRIs. You have others, I can't tell you all the names, but the MRI is basically measuring this. You send things through, a magnetic field is going through, and then different densities or other things that are happening, you can measure and make images that way. Just like you do with sonar, which is what y'all are going to be doing. Sound waves, you do it with magnetic fields.
So PET scans do the same?
What's that?
PET scan.
And PET scan, I just don't know what PET stands for. It's probably electron is the E.
Yeah.
I don't know what the...
Some magnetic, electromagnetic, something. Yeah.
Yeah. So yeah, all those things are using things like this. Okay. It may not be electron beam. Could possibly be a proton beam, but I doubt it. I thought maybe the P was proton, but I bet you it's electron transfer. You might be able to Google it and see what PET stands for. But CAT scans that just stands for computer aided tomography. Okay. Computer aided tomography, I think is what that means. Which you're sending a beam through, and the computer's just mapping it for you. But it's probably an electron beam or something like that. Okay? So that's all there is in 18.7, so there's really no problems there. There's only two formulas in the chapter, and we've hit them both. They're the magnetic field strengths of a single wire and of a solenoid coil. We hit them both earlier. Your review problems, are very few of them, but you could do 1, 3, 5, and that's all. The rest of them, that's all they got. And we did all those in section 17.2, I think, 18.2. Okay? There is another blurb here. Let's see if there's any more. Nope, that's it. So I think we will get to start in 19. Now, chapter 19, how are we doing on time? Oh, we got half an hour left. Let's see what we can do. We're supposed to only do 19.3 and 19.5. So let me get to 19. I'll point anything. Well, that's not the right slide. That's what I want to hit. Okay.
Oh, yeah, I done it. Oh, okay. Because this one Alicia was saying that they added that. She was like, it wasn't on there first. I was like, yeah, I would have done it. It's easy. Take them I think Dr. Wilson teacher. How you doing? I had been to medical school. Oh.
Okay. Did you find what PET was? I know y'all were looking.
It says, positron.
Positron?
Positron.
Positron.
Emission
Say again?
tomograph.
Positron?
Positron emission tomograph.
Tomography. Okay. Okay, got it. Or tomograph would be fine too. That's
Yeah.
the same T as in CAT scan. That's computer-aided tomography, I think is what it is, computer-assisted or something like that. And PET scan is a positron, which is a very interesting concept. A positron is an elementary particle that lives inside a nucleus of an atom that has the same mass as an electron, but it has a positive charge, not a negative charge. And I'm sort of surprised they can produce those at sufficient numbers that you can use it to measure things. But that's pretty interesting.
Yeah.
But again, it's a beam of something. Those would be positrons, just like electrons, except the positrons would be bent in the opposite direction because they're positive charges. The electrons bent on negative charge bent the other way. If I had that slide still up, I've already lost it. Okay. So, chapter 19 is alternating current electricity. Okay? And I'm not absolutely certain why they wanted y'all to have this chapter, but they said it.
Are they following another school's requirements?
What's that?
Are they following another sonography program requirements?
Yeah, well, actually, what happened was when we got the program here, I think one or two other schools in the state were the only two that had it. And they developed this course for these schools to take. And this other school had already started teaching it. And I said, well, what physics book do you use? And they said this one. And that's why we did it. Now, the state came up with the new thing, and that's determined the course description. Remember on the syllabus? They came up with that course description. So I had to pull out from the book the things that match this. And somewhere in there, I can't remember now, it said something about alternating. Oh, well, no, they didn't say alternating current, but they said capacitance and inductance. So that was the chapter where capacitance, inductance, and capacitance is. So I'll try to give you what you need to understand that. But what is alternating current? Well, direct current, all the charges move in one direction. Alternating current, they go back and forth, back and forth, back and forth, back and forth, back and forth. So really, the charges don't move very far at all. They just go back and forth very fast. They just go back and forth. But again, it's not the charges that do anything. It's the energy that the charges have. That's what does the work. That's what provides the light. That's what provides the whatever is happening. Okay? That's what it is, the energy coming from the charges. So alternating current electricity, the charges are just moving back and forth. It's not they're moving through. They're just going back and forth, even in the wire. But everywhere in the circuit, they're all going back and forth at the same speed. So if it's in the light bulb, and they're just going back and forth, and the devices are then using that energy to produce. So that's what alternating current means. And here's how we represent that. Okay? Now, in direct current, we usually show the conductor here and say the current's flowing in that direction. Okay? Or you don't have any current, or it's flowing in that direction. Okay? But what this is doing, alternating current, is changing. So in this place, it's flowing into the right. Here it's zero. Here it's flowing to the left. And here it's flowing to the right again. They didn't show the zero, but you see it's always changing. So the current was going. That's all it's doing. It's not flowing through the wire at all. But guess what? In a direct current circuit, the current's really moving very, very slowly. Even though it comes on almost instantaneously, because it's not the current that matters, it's the field. And as soon as you close the switch, the field throughout the circuit is set up almost instantaneously. Okay? So therefore, it responds almost instantaneously. It's not that the electron moves from the switch to the light bulb. No. The whole field and the whole circuit does, and they all start moving at the same time. So this is what we mean by alternating current. Okay? I'll try to go through this quickly. Okay? This is just a little bit of a reminder, and I don't think we did this for sure, but let me tell you. Power is voltage times current. I don't know if we hit that. I think we did. Power is voltage times current. If this is your power, that's your voltage, and that's the current. If it's direct current, these are all just fixed numbers. But you see, with alternating current, they're always changing. Okay? And if your voltage is doing this, your current is doing this, the power is doing that. Okay? But notice here, positive times positive yields positive. But negative times negative yields positive. So your power is always positive. Your current and your voltage are going back and forth, positive and negative, but because they're going what they call in phase with each other, when the voltage is positive, the current has to be positive because it follows. And when the voltage is negative, the current has to be negative, so they follow, but the power stays positive. So whereas your average current and voltage basically is zero, your average power is somewhere up here. Really, we don't measure current or voltage by average. We do it what we call a root mean squared average, but we won't get into that now. But this is direct current, DC. That's a fixed number, fixed number, fixed number. Okay, usually positive. So there we have it. But this, since the voltage and current is alternating like crazy, the power, though, being the product of the two, stays positive. So you talk about average power. So don't sweat that. You don't need to know it, but just to give you a little background on alternating current. Now, this is your transformer. This is not a transformer. This is an adapter, okay? Converter, whatever you want to call it, okay? Are y'all turning in everything now? Okay.
Are we getting 6
Okay, yeah, let me go run it off then.
Can I get 50?
What's that?
Can I get test 5? I want to hear that.
Okay, you need test 5? You need test 5 also? Okay. It's printed sort of strangely with a, okay, before you go, do you need a test 5 also? Do you need test 5? Okay. Okay. Everybody else got test 5, didn't you? Mm-hmm. Okay, there was a question on test 5. Let me give you, okay, just put that down right there so I'll know where it is. Okay. Number 7 says, what voltage is required to produce a current of 2.85 amps in the circuit below? Someone said, is there supposed to be a picture there? No, it's this circuit they're describing here. With those 3 resistors in series, but rather than a 36 volt source, it's asking what voltage would produce that current. Okay. Now, let me run off test. Okay, wait just a second. Okay. God. Okay.
So we can take you can take that. Yeah.
I was right like 18, 19. So yeah. But I took this class from that's been my school.
But she was there for like she joined it.
But now I know how to work. I didn't know how to work like that. So she broke it down. We get this kind of right. This next. I was like, she's good. Yeah. She's great. She is. That's why I came when she had me in package. She said, I
don't like that rule, but you got it.
She gave me the points and stuff, so it's the formula. It's better than saying, I'm telling you, you need to know something.
Somebody needs
Some
to-
old people
So you look like
probably
you look
tripping
like-
on that. I'm telling you, that's how that's all through that. That tree. Yeah, oh yeah. I know I got no right. Yeah, because when I went to go, she said,
Oh, y'all, you working that problem for real. This part amazing.
that Sabotage. I'm really have to say this is easy once you remember sabotage. With SOH is like hypothesis over, concept or hypothesis. You gonna be yeah. Once you get
Now, we only got 15
I'll
minutes
be
left.
I'm sorry.
Okay.
I'm trying to catch that.
Okay, but listen up. We're not going to get all this covered. Okay? So basically, you can do 1, 2, 3, 4.
I'm listening.
Okay. Don't worry about 5. You can do it if you want to, but you won't lose any points if you miss it or don't do it. Don't do 5 or 6, but you can do 7. I think we'll get 7 done, or an 8. Okay. 9 and 10, I don't think we're going to get to. So basically, 1, 2, 3, 4, 7 and 8. That's it. 1, 2, 3, 4, 7, and 8. That's it. The others, if you want to try, you can. They'll only be bonus. They won't hurt you if you miss them. Okay. Boy, my original got all crinkled up. So. I think y'all nailed them pretty well. Okay. 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 This is crazy. All right. Let's get this covered so you'll know what to do on that last problem. Okay. This slide here is from, and by the way, the last slide here was from 19.2, which we're not doing, but I wanted you to see it. This is also from 19.2, but we'll go on and cover this one, okay? This is what a transformer is. And as I was saying, this is not a transformer. Here's what a transformer does. You have a big problem with electricity in that even in the best conducting wire, there's always some line loss, always some resistance. And the resistance depends on 4 features. One is the type of material. So we always use copper wire because that is the next to the best conductor of any conductors we know about. The best one is silver, but we tend not to use silver wire. I wonder why. Way too expensive. Plus, it's very brittle. Copper wire is very flexible, silver is not. Okay. So we use copper wire. The other feature is the length. Okay? If you have a power plant that's over in Georgia on the Savannah River, south of Augusta, Georgia, and you're sending the current, the power, the electricity to Atlanta to feed Atlanta, yeah, it's a long way. That's at least 150 miles. Well, if you had a lot of current flowing through that, you're going to lose most of that to heat in the wire. So you have a problem there. Another thing is the diameter of the wire. So they make the wire as big as they can get away with without weighing down the poles. That's why they put the big super steel things there, and they hold pretty heavy wires. The next thing, besides the material, the length, and the area, is the temperature. And of course, the more friction you have in there, the higher the temperature, the more resistance. So that's a bad thing. So how can they get around that? Well, it's the current, the amount of charge going through the wire that's creating all that heat and losing it. So if they can drop the current and raise you then don't have as much loss. And let me go back to this slide right here, and here it is. Voltage times current equals power. Now it's the same power throughout, but if you can raise the current, the voltage, you drop the current and now you don't have as much line loss. Then that gives you very high voltage lines, which people don't like to be around. They can really do some shocking, okay? So what they do at the power stations where they're manufacturing the power, they step up the voltage, dropping the current, send it for long distances with hardly any line loss, but then when it gets back to your house or your apartment or the building here, okay, look outside at the power pole and you're going to see this big sort of roundish looking thing hanging on the power pole. That's a transformer. And here's what a transformer does. Okay? You have the primary coil on this side and the secondary coil on that side. And if you're sending in very high energy, high voltage, you put a lot of coils here and very few coils there. Now remember what we said about electricity and magnetism? A moving charge creates an magnetic field. So here you have your AC source here. And this is constantly changing because it's going back and forth, back and forth, back and forth. So you're creating moving charge, great deal of moving charge, and that creates a magnetic field in your core. And then that magnetic field is picked up by the changing magnetic core here, produces current in this side. AC is over here, you don't have anything here but the load, but this is producing the field. But this is a drop-down voltage, a stepped-up current. So therefore, real close to your house where you don't have a long distance to go, you can drop down the voltage, step up the current, so the voltage isn't nearly as high, and you drop your voltage, the current down to, the voltage down to about 120, 110, something like that, which is all our appliances run on that pretty well, except our air conditioning, the hot water heater, the dryer and the oven and those kind of things that produce a lot of heat, they actually step that up to 240 volts or something around there. So that way there won't be as much current that has to flow through, but you still get a lot of heat. Okay? So this is what your transformer does. Okay? And here is the formula. I don't think they show it on the slide. No. Okay? So here's the formula for it. Let me get my pen set up. This will probably be the last, maybe the last slide. We'll do a couple of problems with this. Okay? Here's the formula you use. The voltage on the primary side, the ratio of the voltage on the primary side to the voltage on the secondary side, or you could call it input, output, whatever you want to do, is equal to the number of turns on the primary side, that ratio to the number of turns on the secondary side. There's your formula. So let's just take a look. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 turns on the primary side, 1, 2, 3, 4, 5 turns on the secondary side. Guess what this is going to do? Step down the voltage by a factor of 2. So if you have 120 volts coming in here, you're going to have 60 volts coming out here. The power is the same. It's the voltage changes, and when the voltage changes, the current changes. So this current, let's just give me a number. Make up a number. Second? I heard 15 numbers. Okay, what? 15. Okay. If you say you have 15 amps coming in here, then you would have 30 amps here. Because by the same amount you step up the voltage, you step down the current. Or stepping down the voltage, you step it up by the same ratio. So that's what's happening in a transformer.
Is that why like double-sided phone chargers never have the same current of charge?
Now, what's this again?
Like if you get a USB and it got like two things of charge, one is always lower than the other.
One is always what than the other?
Lower.
Lower. I think that's just so you can't plug it in the wrong direction. Is that, if I'm understanding what you're asking?
No, it'll have like the voltage, one will be 1 point something and the other one like 2 point something. Like,
Oh, it could be input and output.
yeah.
Possibly. I don't know for sure, but I wouldn't be surprised if that's not it. Yeah.
No, like say you got a car charger, like and you got the two spots on it for a USB cord. Yeah, some of them be having like different numbers for the voltage. And if you plug it in, plug it in the top, you get 1.5.
Oh, I see.
Bottom, you got 2.0.
Oh, I bet you that is it. Yeah, that's probably, and you better be careful with that. Because in Europe, I don't think Canada, but in Europe, everything runs at 240 rather than 110. Or 120. So therefore, if you plug your cell phone in there, you're liable to blow your cell phone. So before you go, you have to buy adapters, and depending on what country you go to, you need to know what adapter you need. And I bet you it's that type of thing. For people who have different types of devices, they might need one. Do they have different size plugs that go in there?
USB.
That's the same one.
USB, it just got different voltage on it.
Wow. I can't really answer that because I'm not familiar with it, but yeah. In the plugs they have in different countries, they'll actually have different configuration of the plug, so you can't plug an old one, the wrong one in, or if you force it, you're in serious trouble. So let's see. Here is example 4 at the bottom of page 531. Let's see. Okay. For the life of me, I can't see. Okay. This is the, no. This is something else. Okay, we'll use this one. Okay. Looks okay. A transformer on a neon sign has 100 turns in the primary coil. 100 turns. Okay. And 1,500 turns on the secondary coil. Not this one, folks, okay? This will have a lot more. 1,500 turns. I did read that. No, 15,000 turns on the secondary coil, okay? Okay? 100 turns on the primary, 15,000 on the secondary. If the applied voltage to the primary coil is 110 volts on the primary side, what is the secondary voltage? V sub S. What is that? Set up your ratio, and that was what? VP is to VS as NP, and this, by the way, is NP, and this is NS. NP is to NS. Okay? So this was 110 volts here, is to VS, that's our unknown, so I'll just put VS there, is equal to 100 turns as to 15,000 turns. Okay, the turns cancel out, that's why I didn't write it very clearly. Okay, so what you do here is do a cross multiplication. 100 times VS is equal to 110 times 1,500. 15,000. And then what we'll do is divide by 100. Now I'll make this a little easier for you. You can just wipe out 2 zeros there and 2 zeros there and just do 110 times 150. 110 times 150. Only reason I could do that was 100. It really divided easily. 150 times 110. What's your output voltage?
16,500.
16,500 volts, because that's the unit left over. Let's see what they got in the book. 16,500 volts, and if you wanted to write that as a smaller number but a bigger unit, what would that be? Move it 3 places. 3 places represents 1,000, so that would be kilovolts. 16.5 kilovolts. Okay? Now, I didn't know a neon sign had such high voltage. It must really have a high voltage. That's why they can be so bright, I guess.
Oh yeah, when you buy those, they have a sign on it saying if it's dropped or broken.
Yeah.
Like this acid on it. You know, like this stuff is burning.
I bet so. I can believe it now. Boy, it's amazing. Okay, so here's what I was talking about. What is this coil doing? Stepping up the voltage because you got more turns on the secondary side than you did on the primary side. That's like the one we just did. This is a step-up transformer. This is a step-down because you have fewer coils there. This would be like to have a power station to step up the voltage and send it for long distances. Once you got it into town, then this is a step down so you can get it to the neighborhoods and then even step again to get it in your house. Okay. And I'm afraid we're out of time. Okay. So let's, good deal. Thank you.
I'll be having to get my paper.
Second.
I'll be having to get my daughter from practice.
Yeah. Well, it's time anyway, isn't it?
Yeah.
Okay. So let me find, just had them.
When I was leaving at 6, I kept getting there early.
Okay.
Watch, I leave at 6:30, I'll be late.
Okay. You got 5, didn't you?
Yeah, I got
Okay. Everybody got 5?
And you said do
No.
all questions except for 6 and 7?
All right. I'll go over. 5 you do them all, but 6. I'm sorry. Yeah, test 5. This the one this time. I'll go over it again because y'all were hanging in here tight. I appreciate it. I don't know what. We'll have many people we haven't seen in forever.
Hang in here listening.
There's what?
All right.
2 people didn't even show tonight. Okay. So what you do on this, you do 1 through 4. Skip 5 and 6 unless you just want to try it. But then what we just did here was 7 and 8. Skip 9 and 10. We didn't get to that at all.
So
Okay.
1 through 4, 7 and 8.
1, 2, 3, 4, 7, and 8. Exactly. You can try the others if you want. They won't cost you. If you get them wrong, or if you leave them blank, you get bonus if you get them right.
Okay. Alrighty.
All right. I don't know where everybody else was, but I appreciate y'all. Been a great class. Thoroughly enjoyed it, and I'll see you. I guess most of you plan on bringing it by Wednesday, you think? Okay. I'll be here Wednesday from 4:30, 6:30. Right. My old gray cells ain't working too well. Okay. Good deal. And please do the student course evaluations if you haven't done them already.